to discuss the reversed Carnot cycle. Since the Carnot cycle being completely reversible, it is a model of perfection for a refrigeration cycle. There are two important concepts involving reversible cycles. One is no refrigerating cycle may have a coefficient of performance higher than that for a reversible cycle, which would be operated between the same temperatures of source and receiver. And second, all reversible cycles, when operated between the same temperatures, would have the same coefficient of performance. Okay, so now we are going to derive the coefficient of performance considering a reversed Carnot cycle. So we're going to draw the TS diagram. This is our temperature versus the entropy diagram. So this is our high temperature and this is our low temperature. Okay, so this one we have a cycle. So for example, this is our point 1 to point 2, point 1 to point 2, that is considered to be isentropic, and point 2 to point 3, this is considered to be isothermal, and point 3 to point 4, this is isentropic, and point 4 to 1, that is isothermal or equal temperature. So it is considered a reversed Carnot cycle since in the thermal engine we introduced the a Carnot cycle based on the second law of thermodynamics. Know that it states that there is no machine that has 100% efficiency. It has losses, and the model of or the ideal cycle that can be assumed is the Carnot cycle. So here, since we are concerned of lower temperatures or cooling, so the cycle is reversed. So then it is called a reversed Carnot cycle. So considering reversible processes, so we have in our second law of thermodynamics that the equation of the Q or heat is temperature times the delta entropy. So this is equal, Q is equal because it is considered to be reversible. It is completely reversible. Okay, so we have here a straight line by that. So this TL here this is our Q L, and from here to 1, that is our Q H. So we know that we have this work net. Our work net would be QH minus QL. So through this diagram, we can conclude, or we can draw the biographical representation. So this QH minus QL is this one. This is our work net. Okay, this shaded area here, that is our work net. Okay, so since from this point to this point, that is the amount of our QL, and from this point here to this point here is our QH. So we represent Q here as an area. Okay, so this area, the QH minus QL, this area is our work net. So by second law of thermodynamics, we have Q is equivalent to T times the delta S. So therefore, you can say that QL here is temperature L or TL times delta S. So our QL, this would be TL times what? This is S3 minus S2. Okay, and our QH, therefore, this is temperature of H times the TDS, or times the delta S. This is delta S is S4 minus S1. So delta S, S4 minus H1, S1. So by looking at this graph or this diagram here, we have you can take a look that you can observe that the delta S is equal. The delta S here at the lower portion compared to the other portion or the upper portion is equivalent. So therefore, S4 minus S1, this is equivalent to S3 minus S2. Okay, so by the knowledge of our effectiveness of the refrigerator, so we have that the coefficient of performance, or the COP. This is the desired effect. This is the desired effect, QL over the work input, or this is the work net. So this is for ref, considering a Carnot or a reversed Carnot cycle. So the COP of our ref here, this is T L times, what is that? TL S3 minus S2. This is S3 minus S2. Okay, this is over Q. This is QH minus QL. Okay, so this is TL S3 minus S2 over TH. This is our TH is S4 minus S1. Our QH is TH S4 minus S1 minus TL S3 minus S2. So we can factor out, because this delta S, since it is equal, so we have here TL all over TH minus TL times S3 minus S2, and this is S3 minus S2 also. So you can take it out. So the COP of our refrigerator is purely a function of temperature. So that is TL over TH minus TL. So we derive the COP of our refrigerator considering the reversed Carnot cycle, or we can say that it is a Carnot cycle regardless of the direction, whether it is reversed or not. So technically it is reversed. So like in our thermodynamics, as we going to recall, for thermal engines, it is also a function of temperature. Okay, so how about for our heat pump? So the COP of our heat pump, considering Carnot or a reversed Carnot cycle, this we have more concern of this is the desired effect. Is the QH, this is over the work net. Our work net is QH minus QL. So this is QH times the delta S. So we can write that as delta S. This is TH over this is TH minus TL times the delta S. So this will be take this out. So the COP of our heat pump, considering a reversed Carnot cycle, we have here TH over TH minus TL, wherein our TH is the high temperature and our TL is the low temperature. Okay. So let's consider an example here. So determine the COP for a Carnot cycle of refrigerating machine and for a Carnot cycle heat pump operating between a condenser temperature of 86 degrees Fahrenheit and an evaporator temperature of 50 degrees Fahrenheit, 30 degrees Fahrenheit, and 10 degrees Fahrenheit. So we will solve first for the this is our solution. So the COP ref for our Carnot that is a function of temperature, that is TL over TH minus TL. So our TL here, first we will consider the 50 degrees Fahrenheit. So this is 50 plus 460 Rankine. Okay, and this is the conversion for the Rankine. So this is TH is, we have TH is 86 plus, or this is minus 50. Here you need not to there's no need to convert because we have this difference, so this 460 will be a cancel out. Okay, so if you will calculate this one with the use of your calculator, 50 plus 460, that is 510 over 36, and 510 over 36, that is 14.16 is 14.16 or 166 exactly. So we know that the COP is dimensionless, so there is no unit. So that is for the 50 degrees Fahrenheit, and if this is 30 degrees, our TL is 30 degrees, or our evaporator temperature is operating in 30 degrees Fahrenheit. We have the COP ref Carnot for 30 degrees Fahrenheit. This is TL over TH minus TL. This is 30 plus 460 divided by, this is 86 minus 30. So this is 490 over 490 over 56. So 490 over 56, that is 9.75. Or 8.75 rather. You may check it in your calculator. So let's check in our calculator if our answer is correct. That is 490 over 56. So that is correct. 490 over 56 is 8.75. And for if for the 10 degrees Fahrenheit, so COP ref, considering a Carnot, this is Carnot. So we have the 10 degrees, so we have TH, or T is TL minus TL divided by TH minus TL. This is 10 plus 460 divided by 86 minus 86 minus 10. So that is 470 over 76. 470 over 76. That is 6.18. That is 6.18. So we will proceed for computation of the coefficient of performance for our heat pump, considering the given temperatures, that is 86 and 50, 30 and 10. So COP of our heat pump, the COP of our heat pump here, considering a Carnot cycle, this is TH over TH minus TL. So this is 86 plus 460 divided by 86 minus 50. So let's calculate that one. This 86 plus 460 divided by 86 minus 50. So that is 15. Okay, this is 15.166. Okay, so for temperature L, that is 30, so this is 86 plus 460 for the COP, that is TL, is 30. So this is 86 minus 30. So 86 minus 30, that is 9.75. And given TL is 10, You have here 86. You have the COP 86 plus 460 over 86 minus 10. So we have the COP of our heat pump. This is 7.18. Okay, that's the example for a simple example for our competition for the reverse Carnot cycle, considering the two devices, that is the refrigerator and the heat pump.